You keep hearing people say, "We never went to Venus," but that line is already wrong. Humanity has hit, flown past, and orbited Venus with dozens of missions. The United States, the Soviet Union, Europe, Japan all sent hardware there. Some probes missed, some burned up, some worked. But Venus is not an untouched planet. It is a place we reached, then quietly pushed to the side. But before we continue, please subscribe to the channel to give your support. Let's continue. The confusion starts because Venus does not have the same public story that the Moon or Mars has. You see Apollo flags, you see Mars rovers taking selfies. Venus, by contrast, mostly shows up as a bright dot in the sky or as that evil twin of Earth line in a documentary. Go back to the early 1960s and the picture changes. The first successful interplanetary mission in history was not a Mars probe, it was Mariner 2, a flyby of Venus launched by the United States in 1962. The Soviets were firing probes at Venus in the same era, sometimes losing them, sometimes getting data, learning how hard this planet hits back. So when you ask, why did we never go to Venus, the better question is, why did we go hard, early, then almost stop? For a short burst of time, Venus was at the center of the space race. It got flybys, orbiters, atmospheric probes, and landers, all aimed at turning a blurry point of light into a world with numbers, maps, and photographs. The most intense part of that phase was the landings. In 1970, the Soviet mission Venera 7 became the first probe to land on the surface of another planet and send data back. It dropped through the thick atmosphere, hit the surface, and survived roughly 23 minutes before the environment overwhelmed it. Later missions like Venera 13 and Venera 14 in the early 1980s pushed that survival time to about 2 hours. That sounds short, but look at what they were up against. Venus's surface temperature sits around 465 degrees Celsius, about 870 degrees Fahrenheit. The pressure is about 9.3 megapascals, around 93 times Earth's sea level pressure, roughly what you would feel almost 900 meters, about 3,000 feet, under the ocean. That combination, extreme heat plus crushing pressure, means normal spacecraft design does not work. Electronics that are comfortable up to maybe 100 degrees Celsius, about 212 degrees Fahrenheit, start to fail quickly. Materials soften, seals leak, batteries overheat. So the Venera landers were built like compact armored capsules. They were not meant to last for days. They were designed for one job: hit the atmosphere, reach the ground in one piece, send back as much data as possible, then fail in a predictable way when the planet finally wins. While the Soviets were learning how to touch the ground, the United States focused on orbit. In 1978, NASA's Pioneer Venus missions used probes and an orbiter to study the atmosphere and start probing the surface with radar. Then came Magellan, launched in 1989. Magellan carried a radar system, and over the early 1990s, it mapped about 98% of the surface of Venus at resolutions down to a few hundred meters. That is coarse compared to modern Earth images, but for a planet hidden under clouds, it was a huge jump. For the first time, you could see that Venus has vast basalt plains, volcanic features, and highlands twisted by massive forces. From a science point of view, this was gold. From a program manager's point of view, it started to look like closure. In a short period, humanity had taken Venus from unknown to we have global maps, we have atmospheric profiles, we have rocks sampled on the ground. And that's exactly the moment where the long, quiet freeze-out began. Every space agency lives under one rule: the budget is limited, and you cannot do everything at once. After the 1980s and early 1990s, Venus kept walking into the same wall in funding meetings. On one side, you have Mars, with evidence of past rivers and lakes, buried ice, and the constant question, did life ever start there? On the other side, you have the outer moons, with possible subsurface oceans and thick atmospheres that look like natural astrobiology targets. Those places are easy to pitch as maybe habitable, maybe alive, maybe future human destinations. Then Venus comes up. The slide says, same size as Earth, similar mass, but surface temperature around 460 degrees Celsius, surface pressure around 93 bar, atmosphere mostly carbon dioxide with sulfuric acid clouds. The radars already map the surface at a global scale. The landers already confirm the horror on the ground. The atmosphere is extremely dense. On paper, the science is still strong, but the story is harder to sell. It's not "we might find the fossil" or "we might sail a probe through an alien ocean." It's "we will drop a robot into an oven and watch how it dies." That's how Venus slipped from the front of the line to the back. Missions didn't stop because the planet became boring. They slowed because Venus got labeled as understood enough, while other planets looked like fresher, more flexible targets, especially when you want public support. Mars could be framed as a future home, even if that's very optimistic. Venus could only be framed as a warning. So now you're left with a strange picture. Venus is the planet closest to Earth in size and mass, but it has the most hostile surface conditions we've ever tried to operate in. We've already landed there more than once. We've already orbited and mapped it, but for decades we did not return with new landers. The gap is not in our abilities, it's in our choices. Technically, we can go back. Financially, we mostly chose not to. So that's where the rest of the story lives, in that gap between what we can do in engineering and what we decide to fund. The early missions proved that Venus is not off limits. It's just expensive and unforgiving. So the next question is simple and uncomfortable. What exactly makes this surface so extreme that even today, with far better technology, space agencies hesitate to commit to it? To answer that, you need to look at what the environment on Venus actually does to hardware, to metal, to electronics, and to any mission that dares to touch the ground. That's where we're going next, into the details of a surface that seems to crush, melt, and corrode every piece of equipment you send there. Here's the simple, brutal truth about Venus. The surface is so extreme that it makes normal spacecraft design almost pointless. You're not just dealing with hotter than Earth or thicker air. You're dealing with an environment that pushes heat, pressure, and chemistry all the way to the edge of what materials and electronics can handle. This is the part of the story most people skip, but it's exactly where you see why space agencies keep hesitating even when the science is worth it. Start with temperature, because that alone is already close to a hard stop. The average surface temperature on Venus sits around 740 Kelvin. That's about 467 degrees Celsius, roughly 872 degrees Fahrenheit. That's hot enough to melt lead, soften many steels, and ruin most solders and glues you would normally use in electronics. Standard spacecraft hardware is designed to work comfortably up to maybe 80 to 125 degrees Celsius. That's around 176 to 257 degrees Fahrenheit. Beyond that, circuits drift out of spec, chips fail, batteries degrade fast. On Venus, you're asking your lander to sit in air that is more than 300 degrees above what normal electronics ever see, continuously, with no nighttime cooldown that really matters. Think about what that does, slowly and then suddenly, to every part of the system. The metal chassis expands, joints and bolts are stressed, lubricants inside mechanical parts break down, cables and insulation harden or crack. Solder, the stuff that literally holds components onto circuit boards, can soften or even flow at these temperatures, so your electronics do not just get hot, they can physically deform and disconnect. You cannot just add a better radiator. You would need a pressure shell and heavy thermal shielding around the entire electronics bay, and that shell has to keep working while the outside sits at oven temperatures, hour after hour. Now stack pressure on top of that. At the surface, the pressure is about 93 bar, roughly 93 times the pressure at sea level on Earth. That is equivalent to being almost 900 meters underwater, close to 3,000 feet. Deep-sea submersibles that work at those depths use thick titanium or steel hulls, carefully shaped and tested. And even then, engineers worry constantly about cracks and failure. A thin aluminum lander, the kind you can get away with on Mars or the Moon, would simply buckle and collapse. On Venus, every square meter of your lander is carrying millions of newtons of force from the atmosphere pressing in on it. This changes how you design everything, from the overall body to small details like hatches and connectors. Flat panels want to bow inward. Seals around doors and instrument ports are pushed constantly by that external pressure, so any weakness becomes a leak path. The more you reinforce the structure, the heavier it gets, and the heavier it gets, the more rocket power you need just to launch and land it. Instead of a light science package on legs, you end up with something closer to a compact, armored capsule, where the primary goal is to keep the inside volume at 1 bar, while 93 bar-pounds on the outside, in air that is hotter than a foundry. Temperature and pressure would be bad enough, but the composition of the Venusian atmosphere adds another layer of trouble. The air is about 96.5% carbon dioxide and around 3.5% nitrogen, with sulfur dioxide and other trace gases mixed in. That dense carbon dioxide atmosphere is not breathable, obviously, but from a hardware point of view, the real killer is the chemistry higher up. Between about 30 and 60 kilometers in altitude, there are thick clouds made of concentrated sulfuric acid droplets. Sulfuric acid is extremely corrosive. It reacts with metals, plastics, coatings, and glass. Any probe that has to pass through those layers on the way down or operate in the cloud zone needs special protective coatings on windows, on solar panels, on antenna surfaces, on pretty much everything exposed. Without that, the acid slowly pits, fogs, or eats those surfaces, cutting down light to solar cells, degrading optics, and compromising seals. On Earth, when you design chemical plant equipment, you pick materials very carefully to survive acids and oxidizers. On Venus, you have to apply that same mindset to a flying lab, with strict mass limits and no chance for repairs. All of this comes from one main source, the extreme greenhouse effect. Venus is what happens when you take the basic greenhouse process you worry about on Earth and push it to the maximum. The thick carbon dioxide atmosphere traps heat very efficiently. Sunlight at visible wavelengths comes in, gets absorbed by the surface and lower atmosphere, is re-emitted as infrared, and then that infrared is absorbed and re-emitted over and over again by the dense CO2. The optical depth, meaning how many times those photons get scattered and absorbed before escaping, is huge. The result is that Venus ends up hotter than Mercury at the surface, even though Mercury is closer to the Sun. For climate physics, this is extreme test case mode. If you want to understand where the turnaround point is, where a planet goes from hot but stable to permanent oven, Venus is your main data point. The problem is, to get that data at high quality, you have to put instruments into an environment that is constantly pushing them toward failure. Every temperature sensor, every gas analyzer, every camera has to work in a regime where standard calibration and standard parts do not apply. You do not just run your climate model and say good enough. You need direct measurements from altitudes all the way down to the ground. And that is exactly the range where the environment is most hostile. Put all of this together and you hit the engineering punchline that has blocked Venus over and over. If you want a surface mission that lasts for more than a couple of hours, you need a thick pressure vessel to hold off 93 bar, serious thermal control to keep the inside near room temperature while the outside sits above 460 degrees Celsius, specialized high-temperature electronics that can function at far higher ambient temperatures than normal silicon, and external materials that can resist acid, abrasion, and long-term chemical attack. You're not just scaling up a Mars rover, you're designing something that's part deep-sea sub, part high-temperature furnace hardware, part chemical industry equipment. Every one of those requirements adds cost, risk, and development time. High-temperature electronics use silicon carbide or other exotic materials, which are still more expensive and less mature than normal chips. Pressure vessels must go through intense testing. Protective coatings for acid clouds need years of validation. When mission planners stack all of that up on a spreadsheet next to a simpler Mars lander or a flyby of an icy moon, Venus keeps coming out as the high-cost, high-risk, short-lifetime option. And that's been enough for decades to push it down the list. But here's the catch. If the surface environment is already this extreme, what does the rest of the planet look like? Especially the air that's not just sitting there, but racing around the world faster than the planet turns underneath it. The violence on the ground is only half the story. The other half is in the way the air itself moves, and that's where things get even stranger. Venus does something very strange with its atmosphere. It spins the air around the planet much faster than the planet itself turns. The solid body takes about 243 Earth days to complete one rotation. It's extremely slow. But high up at the cloud tops, roughly 60 to 70 kilometers above the surface, the winds race all the way around the planet in about 4 Earth days. That means speeds around 100 meters per second, roughly 360 kilometers per hour, about 220 miles per hour. You're dealing with a permanent planet-wide high-altitude storm, not occasional weather. For a probe, that means you're entering a flow field that is always in motion, always pushing, always trying to move you sideways as you fall. At roughly Mach 0.3 in that dense air, the relative wind is strong enough to twist parachute lines, push your capsule far from its original path, and load your structure in ways that are hard to predict. You feel the impact of that as soon as you plan a landing. On Mars, you can design an entry, descent, and landing sequence where the probe comes in, uses the thin atmosphere and parachutes to slow down, maybe fire some retro rockets near the end, and hits a landing ellipse that is fairly tight, maybe tens of kilometers across. On Venus, the thick atmosphere and those fast winds mean something very different. As your capsule drops from the upper atmosphere down to the surface, it spends a long time being carried sideways, what engineers call advection. Over that time, these super rotating winds can drag you hundreds or even thousands of kilometers away from the point where you first hit the atmosphere. So you do not say, "We will land inside that specific crater." You basically say, "We will land somewhere on this huge slice of the planet," and accept that uncertainty. That makes mission design harder. If you want to study a certain geological feature like a mountain range or a fracture zone, you cannot guarantee a landing right on it with current tech. You might land on a flat plane instead and just have to live with it. It also complicates communication planning because your relay orbiter or Earth direct link antenna has to be ready to talk to a lander that could end up far from the initial target area. The clouds themselves add another set of problems that goes beyond visibility. Those sulfuric acid clouds between about 30 and 60 kilometers up affect both radio signals and thermal control. As your entry capsule passes through them, the environment around it changes very quickly. Temperature drops to below 0 degrees Celsius, below 32 degrees Fahrenheit in some layers, then climbs to over 400 degrees Celsius, more than 700 degrees Fahrenheit, near the lower atmosphere and surface. Pressure ramps from a few tenths of a bar, less than Earth's sea level, up to more than 90 bar over a vertical range of only 60 to 70 kilometers. So in that descent, your hardware experiences something like this. First, cold, low-pressure conditions where materials contract and batteries cool, then progressively hotter, denser layers where the structure expands and electronics heat up sharply. At the same time, radio waves passing through these layers can bend, scatter, or get partially absorbed. Your link budget has to assume that the signal will lose strength and may fluctuate as the probe falls. You have to make sure antennas, transmit power, and relay geometry can handle those losses, or you risk losing data right when the most interesting measurements are happening. On top of that, the thermal design has to keep the inside of the capsule in a reasonable temperature range, while the outside jumps from cold to extremely hot in minutes. Now, thick air sounds like it should at least give you one advantage: the chance to use aerobraking in entry to save fuel. You might think, great, we can dive into the atmosphere, let drag slow us down, and save on propellant. In reality, Venus makes that trick very risky. When a spacecraft approaches Venus, it is usually moving faster relative to the planet than a similar mission going to Mars, because it has fallen deeper into the sun's gravity well. That higher approach speed means more kinetic energy to get rid of. In a dense atmosphere, that energy gets converted into heat and mechanical loads on the spacecraft very quickly. If your entry path is too shallow, the spacecraft can skip out of the atmosphere, like bouncing off the top layer and heading back into space, which can ruin the plant orbit or even lose the mission. If it's too steep, the heating rate and deceleration can spike to levels that exceed what the structure and heat shield were designed to survive. The safe corridor between skip out and burn up or overstress is narrow. For an orbiter that wants to use repeated passes to lower its orbit, that means you need very accurate navigation, robust heat shielding, and a design that can tolerate high dynamic pressures compared with Mars aerobraking. All of that increases complexity, mass, and therefore cost. So you end up with an atmosphere that gives you only tough choices. It's frick enough to punish you with heating and drag, fast enough to push your lander far from where you aimed, chemically aggressive enough to attack materials on the way down, and stratified enough to make both thermal control and communications a constant challenge. None of these issues is impossible to solve on its own. You can design better heat shields, you can overbuild the structure to handle loads, you can add more powerful radios and better antennas, you can use improved guidance systems to manage the trajectory. But when you combine all of them, you get a clear pattern. Venus looks like a high-risk, high-cost, low-lifetime destination. If you're a mission planner with maybe one flagship mission per decade to spend on a rocky planet, that combination loses against Mars every time. Mars gives you easier entry, more predictable winds, thinner air that still helps you land, and surface conditions where a rover can work for years, not minutes or hours. Venus asks you to accept a serious chance that your probe might fail quickly after a long and expensive development program. That's why the atmosphere that outruns the planet quietly killed long-term Venus campaigns. It didn't do it by breaking the laws of physics. It did it by stacking the odds and costs in a way that made committees say, not this time. And yet, here's the twist. The same hostile atmosphere and insane circulation patterns are also the key to understanding how a planet like Earth can flip from habitable to hellish. The next step in the story is how Venus and Earth started out looking similar, but one of them ended up as the evil twin, and why that should have made Venus the top priority instead of the last choice. How do you take two planets that start almost the same and end up with one that grows forests and cities and one that cooks metal and crushes steel? That's the real shock with Venus. It's not some weird outlier at the edge of the solar system, it's our near twin that went completely off the rails. On paper, Venus looks almost like a copy of Earth. Its diameter is about 95% of Earth's, its mass is around 82% of Earth's, and the gravity at the surface is roughly 8.87 meters per second squared, compared to Earth's 9.81. To you, standing there, it would feel like about 0.9 g, not some low-gravity bounce like the moon or an asteroid. Same star, similar orbit, similar bulk walk-in metal mix. If I only showed you those numbers, no pictures, no atmosphere data, you'd probably say, that sounds like an excellent second home. Just adjust the air a bit and we're good. So how do you get from perfect second home on paper to place where landers die in under 2 hours? The answer most researchers now lean towards is that Venus wasn't always like this. There's a strong possibility that early in its history, Venus had liquid water on its surface. Not a few ponds, but actual oceans, lasting hundreds of millions of years, maybe over 1 billion years. In that phase, the surface temperature would have been low enough for water to stay liquid, clouds to form, rain to fall, and a normal-looking water cycle to run. We do not have direct pictures of waves on a Venusian ocean, but we do have clues. One of the big ones is the ratio of deuterium to normal hydrogen in the atmosphere, which is skewed in a way that suggests a lot of lighter hydrogen escaped over time, as you would expect if huge amounts of water were broken apart high up. Climate models, when you plug in an early, dimmer sun and a wetter Venus, converge on scenarios where the planet is at least marginally habitable for a very long time. So when you look at present-day Venus, you are probably not just seeing a random hell world. You are looking at a world that may have once been as calm and blue as Earth, and then slid into a completely different state. In other words, you are looking at a possible future, not just a curiosity. So, what flips a planet from wet and possibly mild into runaway oven? The key concept here is a runaway greenhouse effect, and it really is a kind of planetary death switch. As the sun ages, it slowly brightens. That means more energy hitting both Earth and Venus over time. On a wet planet, more incoming energy means more evaporation from the oceans. Water vapor itself is a powerful greenhouse gas, stronger per molecule than carbon dioxide. So a bit more sunlight gives you a bit more water vapor, which traps more heat, which evaporates more water, and so on. For a while, this feedback can still settle into a stable balance. But once the amount of water vapor and heat gets high enough, you cross a threshold. The oceans are no longer stable liquid reservoirs. They start to boil away into a thick steam atmosphere. At that point, the planet does not just get warmer, it steps into a new regime. High in the atmosphere, ultraviolet light from the sun breaks water molecules apart. Hydrogen, being light, escapes to space. Oxygen either reacts with the surface rocks or ends up in other compounds. Over long periods, the planet simply loses its water inventory. You go from a world with seas and clouds to a dry world with a thick, mostly carbon dioxide atmosphere and almost no water left. Once you lose that water, you cannot easily get it back. The greenhouse effect locks in, and the surface temperature stays extreme for geologic timescales. If you care about where Earth fits in that story, Venus should be the first place you look. Same general size, similar gravity, similar starting materials, same sun, but a completely different ending. That makes it the perfect laboratory for climate physics at the high end. On Earth, we debate tipping points and long-term risks in models and simulations. On Venus, that tipping point already happened. The data locked in its atmosphere, clouds, and rocks tell you how a real planet behaved when pushed hard. For things like long-term climate sensitivity, atmospheric escape, cloud feedbacks, and the chemistry of hot, dense atmospheres, Venus is the stress test you cannot run on Earth. This isn't just about Earth either. When you look at exoplanets around other stars, a lot of the worlds that are close to Earth-sized and in the right zone may actually be more like Venus than like us. Thick atmospheres, strong greenhouse, maybe past oceans that are now gone. To interpret the light from those planets correctly, you need to understand in detail how a Venus-type atmosphere looks and behaves. Every measurement you can get from Venus, from the deep atmosphere up to the cloud tops, sharpens your filters for spotting real Earth twins and separating them from disguised Venus copies. With all that, you would think Venus would be at the front of the line for missions. Same scale as Earth, extreme climate outcome, huge relevance to our future and to exoplanets. But that is not how the psychology played out. Space agencies do not just sell missions to scientists, they have to sell them to the public, to people who want a positive, hopeful story. For decades, the easiest narrative to sell was simple: go to the place we might colonize. Mars is cold, but it has ice. It has a day length close to 24 hours. It looks like something you could, in theory, make livable. That makes it easy to pitch as fixable. You can draw concept art of bases and cities, talk about future generations living there, and people get excited. Venus does not cooperate with that story. It forces you to talk about failure and limits. The message is not, here is our next home. The message is, here is what happens if a planet runs past its climate stability zone and never comes back. That is powerful for scientists and for anyone thinking seriously about long-term survival. But it's harder to put on a poster and call it the next big step for humanity. So, over time, Venus got framed as the evil twin, useful mainly as a warning, while Mars stayed the good twin, the one you dream about visiting. That framing had consequences. It fed into which mission concepts got momentum, which ones got cut early, and which ones made it through long review processes. The twin that had the most to teach us about how Earth-like planets fail ended up pushed down the priority list again and again. And once psychology tilts like that, money follows. In the next part, we'll dig into how budgets lock those choices in place and why We Never Went Back to Venus is at the deepest level of funding story as much as a physics story. Here's the uncomfortable part. The main thing keeping us from going back to Venus isn't distance or even technology. It's money. The physics is brutal, yes, but the real wall is that every time someone tries to sell a Venus mission, they're walking into a room where the budget is already spoken for. NASA's planetary science pod has to cover everything: Mars orbiters and rovers, missions to Jupiter and Saturn, probes to asteroids and comets, small missions, technology demos, and now huge sample return projects. In practice, that means you get maybe 1 or 2 truly big flagship missions per decade, not 10, not 5. Everything else has to fight for scraps as medium or small missions. So right away, Venus is not competing in a vacuum. It's competing in a lineup of worlds that all want that same rare, expensive slot. So if you only get 1 or 2 shots in 10 years, who gets them? The planet that kills your lander in under 2 hours, or the one that lets your rover run for 15 years straight? That's where Venus keeps losing. Mars sells itself. It has dried up river valleys, sedimentary layers, clear evidence that liquid water once flowed on the surface. You can point to places where a lake shoreline probably existed and say maybe fossils, maybe preserved organics, maybe even extant microbes underground. Europa and Enceladus have subsurface oceans under ice shells, with active plumes spraying material into space. Titan has lakes and seas of liquid hydrocarbons, a thick nitrogen atmosphere, and surface temperatures where methane behaves like water. All of those are easy to pitch as potential habitats, alien oceans, early Earth analogs. Then someone stands up and says, Venus offers lava plains at around 460 degrees Celsius, about 860 degrees Fahrenheit, under 90 plus bar of pressure. Scientifically, that's huge. It's a natural extreme greenhouse experiment, a whole planet that went over the edge. But to a non-specialist, it sounds like we want to spend billions to drop a robot in an oven full of toxic gas, and it will probably die in an afternoon. Mars gives you pictures of sunsets and dust devils. Titan gives you orange skies and lakes. Europa gives you the fantasy of an alien ocean with something swimming in it. Venus gives you melted metal and crushed landers. When you put those side by side on slides, the emotional reaction is obvious. And even if you get past that first impression, Venus then hits you with the cost of simply staying alive there for any meaningful amount of time. On Mars, you can build a lander or rover mostly using ruggedized versions of commercial electronics, the kind of silicon chips industry already knows how to make in huge quantities. You design a thermal system to handle cold, dust, and maybe hot afternoons around 0 degrees Celsius, 32 degrees Fahrenheit, but you are still in a range where batteries, wires, and circuit boards are happy if you insulate them and keep them out of direct sun. On Venus, that fails instantly. If you want a lander to last days instead of minutes, you cannot rely on standard electronics at all. You need high-temperature electronics, often based on materials like silicon carbide that can survive at 200, 300, maybe even 400 degrees Celsius. That's 400 to 750 Fahrenheit. Those technologies exist in labs and in some industrial uses, but they are not mass-produced at the same level as normal chips. They're more expensive, harder to integrate, and less mature. On top of that, you need advanced thermal management inside the lander, phase-change materials that soak up heat as they melt, or even active refrigeration systems that pump heat out of the electronics bay while the outside air tries to cook it. All of that adds mass, volume, and design complexity. And remember the pressure vessel from before? The shell that has to hold 1 bar inside while 93 bars sits outside? That has to be thick, precise, and heavily tested. Every cable feed through, every sensor port, every window for a camera becomes a high-risk penetration in a pressure wall. You cannot afford leaks. You cannot afford small cracks. So you throw even more engineering time and money at it. Step back and compare. A Mars lander can reuse components and design patterns from previous missions, can use commercial-grade chips with some hardening, can ride on launch vehicles and entry systems that are now well understood. A Venus lander, for serious long-duration work, ends up being custom from top to bottom. So when a mission cost team draws their curves, the Venus bar shoots up higher and faster than the Mars bar for the same class of mission. That doesn't mean it's impossible. It means that in the same budget, you might get one Venus lander that survives for hours, or a Mars rover that drives for a decade. When people have to pick, they often pick the longer-lived, lower-risk option. Even when Venus actually wins a competition on science merit, the budget gravity still pulls it down. NASA did finally select 2 major Venus missions, VERITAS, an orbiter to remap the surface and study geology and interior processes, and DAVINCI, a probe that will dive through the atmosphere and image tessera terrain on the way down. On paper, that looked like a real comeback, a sign that Venus was finally getting attention again. But almost immediately, both missions ran into schedule stress because the overall science budget was stretched by other projects, especially big commitments like Mars sample return. VERITAS was delayed, pushed back in favor of missions that were already further along. DAVINCI and related work had to be carefully staged around funding uncertainties. On top of that, every year or two, there are moves to cut NASA's science budget in general. And when that happens, missions that have not yet launched are the easiest targets. A Venus mission that is still in development can be slowed, stretched, or even canceled without the kind of public backlash you would get if you killed a famous Mars rover already on the surface. So Venus ends up living on the edge of the spreadsheet, always one bad budget year away from another long pause. This is where the cold answer shows up. When you ask, why didn't we go back to Venus? Part of the answer is physics makes it hard, but the deeper answer is opportunity cost. Every dollar you put into a Venus mission is a dollar you are not putting into Mars samples or Europa ocean probes or telescopes to look at exoplanet atmospheres. On paper, all these missions look amazing. In the real world, they are in direct competition. Venus has not only been beaten by high temperature and high pressure, it has been beaten by PowerPoint slides that say, look, this other target might have life, or this rover will send back pictures for 10 years. And that brings you to the next question. Even if someone finally wins the budget fight for Venus, do we actually have the hardware ready, or are we still paying for the fact that the last people who really mastered Venus landers were the Soviet engineers of the Venera era? That technical gap, that Venera tech wall, is the next barrier we need to talk about. How do you design a machine knowing the planet will probably kill it in 90 minutes and still call that a success? That's basically what the Soviet engineers did with the Venera landers. They looked at the numbers for Venus, 460 plus degrees Celsius, around 860 Fahrenheit, 93 bar of pressure, and they accepted that nothing was going to live long down there. So they built these landers like armored capsules, thick spherical pressure vessels, high temperature alloys, almost no moving parts. The goal was not operate for months. The goal was hit the surface, stay in one piece, send back as much data as possible in about an hour, then die. That mindset still shapes how people think about modern Venus landers, because it reminds you, the baseline is not long-lived rover, it's shotgun blast of data before thermal death. But even if you build a thick metal shell, what's the point if the brains inside just melt? So how did they keep the electronics working at all? The Venera landers did not use the kind of chips you find in a phone or a laptop today. Modern silicon electronics like to sit near room temperature, maybe up to 100 or 120 degrees Celsius. That's about 250 Fahrenheit, before they drift out of spec or fail. Inside a Venus lander, even with a pressure vessel and insulation, internal temperatures tend to climb far above that as heat leaks in. The Soviet teams had to use specially designed electronics that could operate at much higher temperatures with very simple, robust circuits, no high-speed processors, no complex memory stacks. It was more like industrial control gear than a modern computer. If you try to build a high-performance Venus lander today, you run into that wall again. To put advanced digital systems directly into a hot environment, you need electronics based on materials like silicon carbide or gallium nitride. Those can keep functioning at 200, 300, maybe even 400 degrees Celsius. That's 400 to 570 plus Fahrenheit. But these devices are still emerging technologies, far more expensive and less mature than standard silicon. You can't just go to a commercial supplier and order a full suite of high-temperature processors, memory, and controllers. You have to custom design, custom test, and accept that you're pushing the limits of what's been flown before. And even with hot-tolerant electronics, you still have one basic problem. The environment is constantly dumping heat into your lander. So how do you stop the inside from turning into an oven anyway? One tool you have is thermal buffering, packing the lander with phase change material, substances that melt or change state and absorb a lot of heat in the process. While that material melts, it soaks up energy, keeping the internal temperature lower for longer. It's like giving yourself a thermal battery. You store heat in the material instead of letting it hit your electronics immediately. The catch is, every kilogram of that material is a kilogram you are not using for instruments, communications gear, or structural reinforcement. You're trading science payload for survival time. On Venus, the external environment is trying to pump hundreds of watts of heat into your hardware continuously. The temperature difference between the inside and the outside is huge, so heat flows in aggressively. Insulation slows it down but cannot stop it. Phase change material delays the rise but eventually saturates. If you want to go beyond a few hours, you start looking at active cooling, refrigeration systems that move heat from inside to outside. But now you're adding pumps, working fluids, radiators, or heat exchangers, all of which must operate under 93 bar in a super hot, corrosive atmosphere. Every solution pulls you deeper into complex thermodynamics, where mass, power, and reliability all fight each other. And even if you somehow manage the structure and the heat, you still have another basic question. What is actually powering this thing on the surface? Solar panels seem like the obvious answer for a planet closer to the sun than Earth, but Venus cheats. The thick atmosphere and permanent cloud deck scatter and absorb sunlight. By the time you reach the surface, the available solar power is cut down drastically. Instead of something near 1,000 watts per square meter at the top of Earth's atmosphere, you might only get tens of watts per square meter at the ground on Venus. That's too little to run a serious lander with active cooling and strong radios, especially when you factor in dust, haze, and degradation over time. So, mission designers are pushed toward other power sources, like radioisotope systems, which use the heat from radioactive decay, or very specialized high-temperature batteries. Radioisotope power units are sensitive. They involve nuclear material, strict safety rules, and international scrutiny. High-temperature batteries are a serious engineering challenge. They need to retain capacity and stability at hundreds of degrees Celsius. Either route raises cost and complexity. You can't just bolt on commercial solar panels and lithium-ion packs and hope for the best. Those would degrade or fail very fast in the Venusian conditions. At this point, you might say, fine, we know it's hard. Why don't we just copy what the Venera program did and upgrade it with modern tech? That's where you hit the Venera tech wall. The know-how for those landers, the detailed design methods, test procedures, and hard-earned tricks sits mostly in Soviet and Russian archives and institutions. Western space agencies did not build that hardware. They watched it from the outside. So if NASA or ESA wants a long-duration Venus lander today, they are not refining a proven internal design. They're effectively starting close to zero for this specific environment. They have to reinvent high-temperature pressure vessels for Venus, reinvent the electronic stack, reinvent the test campaigns for 460 degrees, 93 bar conditions. In space engineering, that first-of-a-kind step always comes with a huge price tag. You pay in time, money, and risk. The first mission to use that new tech has to carry the development cost for the whole architecture. Later missions can reuse it cheaper, but someone has to go first. When Venus goes up against Mars or the icy moons in a mission selection round, this is a big handicap. Mars missions can lean heavily on decades of previous rovers and landers. Saturn and Jupiter missions can lean on previous outer planet craft. Venus, for serious surface work, still needs that initial technology rebuild. On a chart, that makes the Venus proposal look eye-wateringly expensive and high risk compared with concepts that use established hardware. So you get this double hit. The planet is physically brutal and the tech base is rusty or fragmented. Even when the science case is strong, the engineering heritage gap makes Venus look like a bad bet to people deciding where to spend limited billions. And that leads to the next twist in the story, because on top of all these technical barriers, we also managed to undervalue the science itself. We tagged Venus as low priority, right when it should have been one of the main laboratories for understanding how planets live and die. How do you look at a planet that might still be reshaping its own surface, running an extreme climate experiment, maybe even hosting weird chemistry in Earth-like air, and still call it low priority? That's what happened to Venus, and it's one of the biggest quiet mistakes in modern planetary science. Start with the ground, because even through the clouds, the geology is screaming that this world is not just a dead rock. Radar maps from missions like Magellan show huge lava plains, strange pancake domes, long rifts, and twisted highlands. But here's the key detail. There are surprisingly few impact craters. On a truly ancient, inactive surface, you'd expect billions of years of asteroid and comet hits to leave it heavily cratered, like the Moon or Mercury. On Venus, the count and distribution of craters suggests that a lot of the surface is relatively young, probably on the order of hundreds of millions of years on average, not the full 4 billion plus. That points to some kind of ongoing, or at least recent resurfacing, big episodes where lava floods out, crust gets recycled, or large regions get deformed. The radar features, the fractures, the dome fields, all hint that the planet's interior is still moving heat out in a serious way. In other words, you're looking at a world that might still be geologically active today, not just in the deep interior, but at or near the surface. If you care about how Earth-sized planets get rid of heat, build crust, and maybe run something like plate tectonics or a different style of tectonics, this is a crucial data point, and right now, most of that interpretation is being done from orbit, with no modern landers to ground truth it. Then there's the bigger question. Is that activity still happening right now while you're watching? Several datasets from orbiters have hinted at thermal anomalies, places that look hotter than expected, or changes in radar reflectivity and emissivity over time, which might mean fresh lava or surface alteration. The evidence is still being debated, but there are strong suggestions that some volcanoes on Venus are not just ancient relics, they may be erupting or oozing lava in the present day. If that's true, it means Venus is constantly pumping gases into its atmosphere, including sulfur compounds and possibly other volatiles, and those emissions are adjusting the climate in real time. That would make Venus a live laboratory for feedback between volcanism and atmosphere. On Earth, you see that when big eruptions inject aerosols into the stratosphere, cooling the planet for a few years, or when long-term volcanic outgassing affects carbon dioxide levels. On Venus, the whole system is cranked up: denser air, higher temperatures, more intense chemistry. If you want to test models of how heat cycles couple to climate, Venus gives you a planet-sized experiment already running. But right now, you're basically squinting at radar changes and thermal hints from orbit, and arguing over them because you don't have landers or long-lived atmospheric probes sitting right on top of those regions. Shift your attention upward into the atmosphere and the science value jumps again. Venus's atmosphere has about 90 times the mass of Earth's air. That means even small changes in composition and circulation can have huge effects on temperature, cloud structure, and dynamics. It's like a climate modeler's stress test, a full 3D fluid shell, thick, hot, and chemically complex. If you can measure how temperature, pressure, composition, and wind speed change with height and latitude, from the deep layers near the ground all the way up through the clouds and into the upper atmosphere, you get a dataset that lets you push your theories of circulation and climate far beyond Earth conditions. On Earth, you can't ethically crank the greenhouse effect up until the oceans threaten to boil just to see what happens. On Venus, that limit has already been crossed. By sending probes that profile the atmosphere on the way down, or balloons that ride the winds at different altitudes, you can watch how heat moves, how jets and waves form, how clouds respond when you're way past normal Earth ranges. That doesn't just refine Venus models, it feeds directly back into understanding extreme climates on exoplanets and into the high-end bounds of Earth's own climate over long timescales. Now comes the part that would sound like science fiction if it hadn't already shown up in serious papers: the question of astrobiology in the clouds. Deep down at the surface, conditions are so hot and dense that life as we know it has no realistic chance. But higher up, around 50 to 60 kilometers above the surface, the story changes sharply. In that band, temperatures range roughly from 20 to 60 degrees Celsius, about 68 to 140 degrees Fahrenheit, and the pressure is about half to 1 bar, similar to conditions you experience on Earth at sea level or in the lower mountains. In other words, there's a Goldilocks layer of air where, purely in terms of temperature and pressure, life would not instantly be destroyed. The problem is that layer is filled with sulfuric acid droplets and an atmosphere rich in carbon dioxide and sulfur compounds. But some researchers have pointed out that, on Earth, there are microbes that tolerate acid, live in clouds, and use chemical pathways that don't look like the familiar oxygen-based metabolism. So people started to ask, very carefully, could airborne microbial life exist in the temperate clouds of Venus, using sulfur chemistry, floating in droplets, reproducing slowly, and leaving subtle chemical fingerprints? It's speculative, and no one has proof, but it's a real astrobiology question, not just a wild guess. Some unexplained features in the way Venus's clouds absorb ultraviolet light and in their detailed chemistry keep that discussion alive. If that scenario is even 10% plausible, then cloud layer probes, balloons, or aircraft that scoop and analyze droplets become incredibly high-value missions. You'd be checking not just for life on Venus, but for the range of environments where life can exist at all. You'd be testing whether surface habitability is the only game in town, or whether a planet that lost its oceans and cooked its ground might still host something in its skies. Stack all of this up: active or recent geology, possible current volcanism, a massive atmosphere that is the ultimate climate stress test, and a temperate cloud layer that poses serious questions about chemistry and maybe life, and you'd expect Venus to sit near the top of every priority list. For pure science per kilogram sent, it looks very strong, but that's not how it was treated for a long time. For decades, when expert panels and decadal surveys scored potential missions, Venus kept ending up behind Mars, behind the outer planets, behind asteroid and comet missions. Not because its science case was weak, but because of everything you've just walked through in the last few sections. The high cost of surviving on the surface, the risk of short mission lifetimes, the lack of an easy "we might live there" story, and the perception that there was no obvious life on the surface. When people saw that combination, they gave Venus solid scientific marks, then quietly pushed it down the list in favor of targets that looked cheaper, safer, or more photogenic. That misscoring is a big part of why we never really went back. The most Earth-like planet in size, the one with the most extreme climate outcome, and one of the most interesting atmospheres in the solar system was treated like an optional bonus, not a core target. And the irony gets worse, because even in the part of Venus that is most friendly to hardware, the cloud deck, we still walked away from mission concepts that could run for weeks or months in near-Earth conditions. That missed opportunity in the clouds is the next piece of the puzzle. How can the most hellish planet you know also have a layer that feels almost comfortable to you? That's the twist in Venus's atmosphere that almost no one outside the field thinks about. Down on the ground, you have 460 plus degrees Celsius, 90 plus bar, metal melting conditions, but go up to around 50 to 60 kilometers altitude and the story flips. At roughly 55 kilometers, pressure drops to about 0.5 to 1 bar, similar to Earth at sea level or up in the lower mountains. Temperatures sit in the range of 20 to 70 degrees Celsius, about 68 to 160 Fahrenheit. That's hot, but it's not a lead-melting inferno. It's something your hardware can actually handle with standard high-temperature design. In that Goldilocks band, the air is still mostly carbon dioxide with sulfuric acid droplets, so you are not walking around in shirt sleeves. But in terms of basic physics, pressure and temperature, this region looks familiar. You don't need thick titanium pressure holes. You don't need every component to survive 460 degrees. You can design balloons, aircraft, or long-duration platforms using materials that already exist for harsh Earth environments, like high-grade polymers, corrosion-resistant alloys, and standard high-temperature electronics kept inside insulated pods. Suddenly, instead of fighting both heat and pressure at the limit, you're fighting mainly chemistry and wind, which is tough, but not insane. The key point is, this is not a fantasy concept. Balloons in the Venus atmosphere are not just concept art. In 1985, the Soviet Vega missions actually did it. Each spacecraft carried a lander and a balloon probe. When they hit the atmosphere, they deployed the balloons at around 54 kilometers altitude. Those balloons inflated, caught the wind, and floated in the Venusian cloud layer for about 46 hours. They rode winds of roughly 240 kilometers per hour, around 150 miles per hour, circling part of the planet and sending back data on pressure, temperature, and wind speeds. That is your proof of concept in real hardware. A platform can live in the clouds of Venus for nearly 2 days using technology from the mid-1980s with limited computing power and basic materials. If you apply modern material science, better coatings against acid, lighter structural fabrics, better batteries, and smarter avionics, you can reasonably expect to extend that lifetime from days to weeks, maybe longer. You could design fleets of balloons or gliders, some at 55 kilometers, some higher, mapping the atmosphere in 3 dimensions over time, measuring chemistry, winds, and maybe even sampling droplets directly. So why is that layer still so mysterious? because the chemistry there does not cooperate with simple models. Those clouds are full of sulfuric acid droplets, sulfur dioxide, and a mix of other trace gases. When you look at Venus through ultraviolet and visible light, you see dark and bright patterns in the clouds that do not map cleanly onto any one known substance. Some wavelengths are absorbed more than you expect, some less. Researchers have tried to explain these features with different mixtures of sulfur compounds, aerosols, and complex particles, and while you can fit parts of the spectrum, there are still pieces that do not fit neatly. That's why in peer-reviewed work, people have cautiously raised the possibility of unknown absorbers, and a few have asked whether unusual forms of chemistry, maybe even involving microbial life, could be part of the explanation. The idea is not Earth-style life floating happily in the sky. It's more like if you have droplets, moderate temperatures, energy sources from sunlight and redox chemistry, and long timescales, could something tiny and robust evolve to use sulfur chemistry in that layer? No one has evidence yet, but the open questions in the spectra and the weird behavior of the UV-absorbing stuff keep that door from closing completely. From a mission planning perspective, that makes the Venus cloud deck insanely interesting. You could send a balloon or aircraft that samples droplets and gas, runs onboard mass spectrometers and microscopes, and directly looks for complex organics, unusual particles, or any signs of non-equilibrium chemistry. And even if you found no biology at all, you would nail down the real composition, size distribution, and optical properties of the aerosols, which feeds back into climate modeling, radiative transfer, and exoplanet interpretation. And you could do it while operating in conditions that are physically much kinder than the surface. Here's the strange part. Balloon missions to Venus actually look relatively affordable on paper compared with heavy lander surfacers. You avoid the worst of the pressure and temperature, you get longer lifetimes, and you can use more off-the-shelf hardware types, as long as you treat the acid problem seriously. Yet, we didn't double down on this architecture. Why not? The short answer is optics. Not in optics in the telescope sense, optics in the how does this look in a press release sense. Balloons and cloud platforms are atmosphere-centric. They give you profiles of gas composition, droplet chemistry, winds, waves, and temperature structures. That's incredibly useful for scientists, but it does not come with the classic, emotionally powerful visuals. No rover selfies, no high-resolution panoramas of rocks and hills, no robotic drills in the soil. Instead, you get instrument readouts, charts, and maybe some hazy images of cloud layers. When those missions had to compete with concepts that promised to drive around on Mars or fly through geyser plumes at Enceladus, the atmospheric focus looked less attractive to people outside the field. In funding meetings, that matters. A Venus balloon that runs for 30 days and transforms our understanding of cloud chemistry can look less compelling to non-experts than a rover rolling around a crater edge that might once have been a lake. Even if the balloon mission is cheaper and lower risk, the wow factor on the surface missions often wins. So the balloon concepts kept getting studied, refined, and then quietly shelved or pushed aside for later, while other missions with more obvious visual payoffs moved forward. That leads straight into the irony at the heart of this whole story. We've basically ignored the one region of Venus where a mission could operate for weeks or months in near Earth-like pressure and temperature using technologies we already know how to build. And we judge the entire planet almost entirely by the conditions on the ground, where everything dies fast. It's like looking at Earth, seeing the temperature and pressure in the deep mantle, and deciding the whole planet must be unworkable, while ignoring the fact that the surface is mild and full of life. On Venus, the kind layer is up in the sky, not down on the ground. But the logic is the same. We let the furnace at the bottom define the entire reputation of the planet, and walked away from the part that would actually let us stay and watch it breathe. And this feeds into the next mistake, because once people convinced themselves we already mapped the surface from orbit, they used that as another excuse to sideline Venus. The radar images from Magellan became a kind of mirage, a story that said we've seen it all, when in reality we'd only scraped the first layer of detail. So the next step is to look at how one radar mission in the 1990s helped lock in this false sense of closure, and why our map of Venus, compared to what we accept for Earth or Mars, is still embarrassingly crude. Magellan made a lot of people think Venus was done, and that's a big part of how it got sidelined. In 1989, NASA launched the Magellan spacecraft, and for its time, it was a monster of a mapper. It used synthetic aperture radar, basically sending radio pulses down through the clouds and building images from the reflected signals. Over its mission, it covered about 98% of Venus's surface at resolutions on the order of 100 to 300 meters per pixel. For the early 1990s, a global radar map like that was a huge achievement. You go from a blank globe under clouds to a full global data set of mountains, plains, and weird structures. So it was easy inside agencies and in the public to say, okay, surface mapped, job done, let's move on to the next planet. Here's the catch. 100 meters per pixel is not actually very detailed. Think about a football field. That's roughly the scale of 1 pixel in many of those maps. You can see big flows, big craters, giant fractures, but not the fine structure. Your phone camera at a few micrometers per pixel at arm's length beats that by orders of magnitude. For Earth, we would never accept 1990s level satellite imagery and say, that's enough, we understand the surface now. We keep sending better and better imagers down to sub-meter resolution because the details matter. On Venus, we stopped at good enough for the 90s and treated it like a finished job. So our best global view of Venus is, by modern standards, blurry. You can see that something happened, but not exactly how. You see broad flows, but not small channels. You see domes and ridges, but not the finer textures that would tell you whether a region is blocky, smooth, layered, or rubble. That means a lot of the work we do on Venus geology is still coarse-grained. We are inferring processes from big patterns, not from tight, detailed contacts like we have on Mars. Then there's the composition problem, which is worse. Radar images are not like color photos. They don't directly tell you what kind of rock you're looking at. Radar brightness, the way a patch reflects radio waves, depends on roughness, slope, and dielectric properties, which might be linked to composition, but in a messy way. So when you see a bright patch in the Magellan data, you can say this is rougher or has different radar properties, but you can't easily say this is definitely fresh basalt or this is a deposit of some exotic mineral without in situ measurements. We have a few old lander samples from the Venera and Vega missions, but those are limited in number and location, and they predate Magellan. So when you stare at the global radar maps and ask what rocks are we actually seeing, the honest answer is, in many cases, we don't know. Is that bright halo around a volcano fresh lava, rough fragmented debris, or something chemically unusual that changes radar reflectivity? Without modern landers or at least low-altitude spectrometers that tie radar signatures to actual rock types, you're guessing. It's informed guessing, sure, but it's still guessing. Now zoom out to the big-scale structures. Venus shows a lot of tectonic-style features. You see long rifts, folded terrains, networks of fractures, and these weird circular to oval features called corona, which look like upwellings or collapses in the crust. Clearly, the planet has been deforming its surface. The big question is how? Earth has plate tectonics, slabs of crust moving, subducting, colliding, recycling over hundreds of millions of years. Mars seems more like a stagnant lid, with localized volcanism but no global plate cycling. Venus might be doing something in between, or something completely different. There are several hypotheses on the table. One idea is that Venus has a stagnant lid most of the time, then occasionally undergoes catastrophic resurfacing events, where large parts of the crust get recycled in bursts. Another is that it has sluggish, patchy tectonics that don't quite become plate tectonics, but still move heat out more actively than Mars. Some models suggest episodic overturn, where the whole lid destabilizes, sinks, and is replaced. The Magellan data show that something like that might have happened, but they don't let you discriminate cleanly between these scenarios. That is a giant unresolved question because it goes straight to how do Earth-sized planets in general lose their internal heat and how unique is Earth's plate tectonics? And yet, because Magellan produced those global maps, a narrative formed that Venus was known terrain. You see that phrase between the lines in old reports: global mapping complete, surface characterized, and so on. Meanwhile, Mars kept getting new orbiters with better cameras, sharper images, and more spectral bands. Every new mission revealed previously hidden river deltas, layered sediments, fresh-looking gullies, and fine-scale structures that told clearer stories about water and climate history. Each improvement made Mars look more dynamic, more detailed, more worth going back to. Venus did not get that constant refresh. No new high-resolution radar mapper came along to sharpen the view. No color imagers in orbit peeled back more layers. So our picture of Venus stayed stuck at early 90s resolution, and the science community outside the Venus specialists started to treat it like understood enough. That asymmetry in data streams, high bandwidth, high resolution updates from Mars versus old static radar maps for Venus, helped Mars stay at the center of attention while Venus faded into the background. This is the Magellan mirage, the illusion that we already mapped it, so we're done, when in reality, our map would embarrass us if it were the best we had for any other major rocky world. And even if you fix that, even if you flew a new radar orbiter and got 10-meter resolution everywhere, you'd still hit another set of issues, because Venus is not just tricky in space, it's tricky in time. The planet spins slowly, the day is longer than the year, communications are awkward, and power cycles become a nightmare. The next hurdle is not just where you look, it's when and how long you can stay awake during a day that lasts almost 4 months. How do you run a mission on a planet where a single day is longer than a year? That is the first problem Venus throws at you that feels almost absurd. Venus rotates once every about 243 Earth days, but it orbits the Sun in about 225 days. That weird combination means the time from one noon to the next noon on the surface, the solar day, is around 117 Earth days. So if you land a probe, daytime is not a simple 12 hours on, 12 hours off. It is almost 4 months of very slow, very steady daylight heating, followed by a very long night. Now, the thick atmosphere means the surface temperature does not swing wildly. The air has so much thermal mass that it smooths out extremes. But the operational reality still changes. You cannot rely on simple cycles that engineers and operations teams are used to. On Mars, a rover team can sync to a roughly 24.6-hour day, and they can plan soul-to-soul operations, with periods of sunlight, battery charging, and nighttime sleep modes. On Venus, those cycles stretch into weeks and months. If you somehow built a lander that could survive long-term and tried to use solar panels, you would have to deal with multi-week periods of low or no sunlight, and multi-week periods where any sun that filters through is steady and relentless. That long day also interacts with power in nasty ways. Because of the clouds and thick atmosphere, the surface already receives much less solar power than you'd expect for a planet closer to the sun, only tens of watts per square meter, instead of something near 1,000 watts per square meter at the top of Earth's atmosphere. Combine that with a 117-day solar cycle, and any solar-based design becomes extremely inefficient and complex. You would need huge panels to gather modest power, plus massive batteries or other storage to cover long, dark stretches. In practice, that pushes you toward radioisotope or other always-on power sources, which, as you heard earlier, are technically harder. Communication becomes another headache. Mars has a whole support network now, orbiters that act as data relays like local cell towers in space. Landers and rovers send data up to those orbiters at relatively short range. Then the orbiters send it back to Earth with bigger antennas and more power. Venus has had far fewer long-lived orbiters, and the combination of slow rotation and thick atmosphere complicates line-of-sight planning. If your lander survives on the surface, there will be times when an orbiter is blocked by the planet or passes overhead at awkward angles, and you can't just count on multiple backups the way you do at Mars. You might have a lander that is physically doing fine, but still effectively mute for long stretches because the geometry doesn't favor good links. Direct-to-Earth communication from the surface is even tougher. You're trying to punch a radio signal through dense, cloudy air across tens of millions of kilometers with a small antenna and limited power. You need deep space network support on Earth, properly timed passes, and a mission profile that expects patchy contact, not constant streaming. It's entirely possible to imagine a future Venus lander that collects very valuable data but can only drip it out in bursts when the orbital alignments cooperate. Even though the surface temperature doesn't swing a lot, that long day length still affects how you manage heat inside the spacecraft. A system that can ride out one hot afternoon is very different from a system that has to endure a slow, continuous heating phase across weeks without any meaningful cooling breaks. Remember, the atmosphere is already pushing hundreds of watts of heat into your lander. Over 100+ days of daytime, even small imbalances between heat in and heat out build up. Your thermal design has to be robust over long times, not just over a short entry and landing. If you somehow built a hybrid system that used both internal storage and external radiators, you'd have to plan for a radiation environment in which the external side is never really cold, and the timing of any small dips and rises does not line up with easy human schedules. You can't say, we'll cool down at night, when night means weeks, and the baseline is still hundreds of degrees Celsius outside. Navigation and mapping also run into the slow rotation problem. On a fast-spinning planet, surface features sweep quickly under an orbiter's ground track. That can be useful for building up repeated coverage, catching different lighting angles, and planning constellations that behave almost like GPS, giving you frequent crossovers and many possible paths. On Venus, surface features move very slowly under the spacecraft because the solid body is barely rotating. That can be good for certain types of radar imaging where you want the same geometry for a while, but it makes quick repeat imaging with sunlight harder, and it makes building a dense network of timing signals like an on-planet navigation system less efficient. The whole dynamic behavior of Venus, rotation, day length, atmosphere movement, is just slightly out of sync with the rhythms we've tuned a lot of our hardware and operations practices. We're used to roughly Earth-length days, or at least reasonable fractions of them. We're used to mission control teams working in daily cycles, matching the planet. Mars's cooperation with human schedules is one of the underrated reasons it is so convenient. You can have engineers on Earth live on Mars time without completely wrecking their lives. Venus does not give you that. You either completely decouple operations from local solar time, or you accept that some phases of the mission will run under very strange lighting and thermal conditions. Put it all together, and you get a planet that is not just hostile to hardware, but hostile to schedules. When planners can choose between a world with a 24.6-hour day, where operations can be run almost like an extended Earth shift, and a world where a solar day is 117 Earth days, they pick the one that fits human and technical routines. The long day on Venus is one more quiet strike against it. One more reason people say, let's go somewhere easier first. But even after you get past the slow spin and the awkward communications, there's a final set of excuses people use, and those sit not in the planet, but in the path you take to get there. Venus looks closer on a simple solar system map, but when you actually calculate the energy, the delta V, and the heat you deal with on the way in, the picture changes. The next step is to look at how getting to Venus and slowing down once you arrive ends up being less of a bargain than it first appears, and how that perception problem became yet another reason to delay going back. Venus tricks you right from the start, even on a simple solar system diagram. On paper, it looks like the easy target. At its closest, Venus can be only about 41 million kilometers from Earth, while a good Mars opposition is more like 55 million kilometers. So you hear closer, and your brain jumps to cheaper, easier, less fuel. But in orbital mechanics, raw distance is not the main thing that matters. The key is how fast you and the planet are moving around the sun and how much you have to speed up or slow down to match. Transfer orbits and relative velocities drive the cost, not just the gap in kilometers. When you send a spacecraft to Venus, you are not just flying straight across a gap, you are dropping inward toward the sun. As you fall closer to the sun, you pick up orbital speed, just like a satellite falling closer to Earth speeds up in its orbit. By the time you reach Venus's orbit, your spacecraft is moving faster than Venus itself in many trajectories. That means your relative speed, the speed difference between the spacecraft and the planet, can be high when you arrive. To get captured into orbit or to have a safe, controlled entry into the atmosphere, you have to get rid of a lot of that speed. Some of that braking can be done by the atmosphere, some by engines. Most missions use a mix. But in terms of pure energy, the total delta V, the change in velocity needed for the whole mission profile, can end up comparable to, or in some designs even higher than, what you'd pay for a Mars mission. From the launch vehicle's point of view, you do not automatically save a lot just because the map says Venus is closer. The energy bookkeeping is more subtle. You get a lower launch energy in some cases, but then you pay for it at arrival with tougher capture burns, heavier heat shields, or both. That extra speed at arrival shows up in the most brutal way during atmospheric entry. The kinetic energy of your spacecraft scales with the square of velocity, so even a modest increase in speed means a lot more energy that has to be dissipated as heat. At Venus, the relative entry speed can be higher than typical Mars entries, and you are hitting a much denser atmosphere, so you decelerate faster over a shorter distance and the heating rate spikes. All that kinetic energy turns into thermal energy in the shock layer around the capsule and in the heat shield itself. Mars entry is already one of the hairiest things we do in planetary exploration. You come in fast into a thin atmosphere that barely gives you enough drag to slow down, and you have to juggle heat, aerodynamics, parachutes, and sometimes rockets. Venus entry takes that and layers extra difficulty on top. You are dumping more energy in less time, and the air around you is thick and hot instead of thin and cold. It's not just more of the same. It's like doing Mars entry, then dropping the last part of the trajectory into a hotter, denser fluid that punishes any miscalculation. Your heat shield has to handle higher peak heating and total heat load, and your structure has to tolerate higher deceleration forces, measured in multiple G for longer. Then there's the timing. Like Mars, Venus has favorable launch windows that open on a regular cycle, roughly every 19 months. That part sounds easy. Wait for a window, launch, cruise, arrive. But mission designers have to add another constraint, the thermal environment during cruise. A probe on its way to Venus spends more time closer to the sun than a probe going to Mars. That means more intense sunlight, higher temperatures on sun-facing surfaces, and stricter limits on how the spacecraft can be oriented and cooled. Components, coatings, radiators, and even simple things like cables and adhesives have to be rated for higher steady heating on the way in. You can't casually take a Mars bus, a standard spacecraft design used for Mars missions, and slap a Venus entry capsule on it. The whole cruise phase, the thermal management, and the final approach all sit in a different regime. You might need larger radiators, different insulation, more robust sun shields, and different kinds of attitude maneuvers to keep temperatures within limits. All of that has to be tested and validated, which means more engineering time and money. On the entry side, you're also designing for a different atmosphere with different density and temperature profiles, so your parachutes, if you even use them, your aeroshell shape, and your guidance system all need fresh work. So even on the trajectory level, Venus keeps refusing to be the cheap option. It's closer in kilometers, but not clearly cheaper in energy or hardware. That creates a perception problem. When you tell a non-specialist, Venus is closer than Mars, they respond with, so it must be cheaper and easier to reach. Why don't we just go there more? Then engineers show the real numbers for delta V, heat shield requirements, structural margins, and high temperature systems, and the answer becomes, actually it's not obviously cheaper, and in many ways it's harder. At that point, the enthusiasm drops. The world that looks like a bargain on a simple solar system poster turns out to be anything but once you factor in capture burns, dense atmosphere entry, cruise heating, and the custom hardware needed to survive the surface. You lose the "it's closer so it's easy" marketing advantage, and you're left with a pitch that says, this is about as hard as Mars or worse, with shorter surface lifetimes and scarier entry. In a room where people are already nervous about risk and cost, that is not the winning slide. Stack that on top of everything else you've seen, the brutal surface, the super rotating winds, the long day, the tech gap, the budget competition, and you can see how we never went back became the default outcome for a long time. The physics lined up to push Venus away, even while new hints kept coming in that maybe, just maybe, its atmosphere was hiding surprises we didn't expect. The next turning point in this story came when one of those surprises blew up into a global argument centered on a single word: phosphine. How does one weird chemical signal, buried in noisy data, drag an entire planet back into the spotlight? That's what happened with phosphine on Venus. In 2020, a team published a paper claiming they detected phosphine, pH3, in the atmosphere of Venus. On Earth, you mostly see phosphine from industrial processes or from microbes in oxygen-poor environments. It's not something that hangs around easily in a hot, oxidizing atmosphere. It gets destroyed. So if you really have phosphine on Venus in measurable amounts, you need a strong source, either some exotic chemistry we don't understand, or some form of life, or a combination of both. The claim came from radio telescope data, looking at a specific spectral line, a fingerprint in how Venus's atmosphere absorbs radio waves. The team processed the data, subtracted noise, corrected for the instrument, and saw a dip they interpreted as phosphine. Very quickly, other groups jumped on the data, or reanalyzed similar observations. Some said the signal was weaker, or gone. Others argued the line could be explained by sulfur dioxide or by processing artifacts. The whole thing turned into a loud, technical argument about calibration, noise, and chemistry. As of now, there's no clean, agreed answer. The detection is controversial, the interpretation is debated, and no one can say phosphine is definitely there with high confidence. But here's the important part. Scientifically, it mattered even if it was wrong. For the first time in decades, Venus sat at the center of a global astrobiology fight. People who had ignored Venus for years suddenly had to read papers about its atmosphere, its clouds, its chemistry. Space agencies and decadal survey panels, the groups that rank mission priorities, had to ask, are we missing something big by treating Venus as a dead, solved world? Venus stopped being just the hot one in the background and reappeared on slides titled Targets for Life Detection, even if the conclusion was probably unlikely, but we should check. That renewed interest pushed attention straight back to the altitude band you've already heard about, roughly 50 to 60 kilometers up, where temperature and pressure are close to Earth-like, 20 to 60 degrees Celsius, around 68 to 140 degrees Fahrenheit, and about 0.5 to 1 bar. The phosphine claim made people look again at older work that had already said there are spectral features in the UV and visible that we don't fully explain. There were already hints of unknown UV absorbers and discussions of whether some unfamiliar sulfur chemistry or complex aerosols or even microbial populations could be responsible. Once phosphine was on the table, those older questions suddenly looked more urgent. If there is even a small chance that unusual chemistry in those clouds is tied to biology, then detailed in situ measurements become extremely valuable. You want cloud-scooping probes, balloons that fly at those altitudes, mass spectrometers capable of separating out different molecules and particles, instruments that can distinguish between purely abiotic chemistry and something more complex. Even if you go in expecting to find nothing alive, the only way to shut down the argument properly is to go there and measure. So why didn't that phosphine flare-up immediately translate into, okay, send landers and balloons right now? Because hype doesn't build hardware. You still have to go through all the steps you've seen already: mission concept studies, cost estimates, technology assessments, approvals, and budget fights. Cloud platforms need corrosion-resistant materials, reliable power sources, and long-duration avionics. High-resolution spectrometers need calibration and test time. Even a relatively simple atmospheric probe can take close to a decade to go from proposal to launch once you factor in all the reviews and funding cycles. The controversy also gave skeptics a convenient line: let's not overreact to one noisy dataset. They could say, we don't cancel all our assumptions every time a single paper claims a biosignature. That is fair from a cautious point of view, but it also made it easier for people who were already cool on Venus to say, interesting, let's wait and see, instead of committing hard money. So you got this strange split, intense media coverage and conference debates, but a slower, more cautious shift in actual mission planning. Even with that drag, the phosphine episode did something important. It moved the Overton window, the range of ideas that are considered acceptable to discuss seriously. Before 2020, if you stood up in a big meeting and said, I think we should look for life in the clouds of Venus, a lot of people would quietly roll their eyes or treat it as fringe. After the phosphine debate, the tone changed. You could still disagree, you could still say, I think it's unlikely, but you couldn't just dismiss the entire idea out of hand. Cloud habitability became a serious, if speculative, topic. Mission concept studies that focused on Venus's atmosphere and cloud layers started to look less like long shots and more like reasonable proposals. Venus, which had been stuck in the "we're basically done there" pile, started to claw its way back toward the center of the table. Panels revisiting planetary priorities began to bump its ranking upward. People realized that between climate physics, extreme geology, and even low-probability astrobiology, the planet carried a lot of weight. The phosphine argument didn't prove life, it didn't resolve the chemistry, but it did break the mental lock that said, Venus is boring and solved. That shift set the stage for the next step, because once Venus is back in serious discussion, the next question is, what do we actually send? And that's where the story turns practical again. Orbital mappers, atmospheric probes, balloons, maybe even long-lived landers, all got another shot at competing for real money. After a long silence, multiple space agencies finally picked Venus missions to move forward. The catch is they're still sitting in an environment where any budget cut can slow them down or kill them before they ever leave the pad. So the next part of the story is about those missions we are finally, slowly sending back to Venus, what they're designed to do, and how fragile their future still is. For the first time in decades, you actually have a new wave of Venus missions lined up, and that should feel like a turning point. But here's the catch. Every single one of them is living in a shaky world where a bad budget year can still knock them over. First, there's the one that directly attacks the Magellan problem, NASA's VERITAS mission. VERITAS is basically Magellan but upgraded to this century. It's an orbiter built to carry a much more advanced radar system, high-precision tracking, and infrared spectroscopy. The plan is to map the surface at much higher resolution than Magellan, build a true global topographic map, and watch for changes that might show active tectonics or current volcanism. It's designed to answer questions Magellan could only hint at, like whether some volcanoes are erupting right now, how thick the crust is, and whether the planet is flexing under the pull of its interior in ways that look like plate tectonics, or something else entirely. VERITAS was delayed during earlier budget stress, then reinstated into NASA's fiscal year 2025 plan, with a target launch around 2031, which is late, but at least it's back on the books. If VERITAS is the fix the map mission, DAVINCI is the go down there and sniff the air mission. DAVINCI, short for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, is built around an orbiter plus a single brutal descent probe. The orbiter does remote sensing and sets up the geometry, but the star of the show is the probe that will hit the atmosphere, slow down, and fall all the way to the surface. On the way down, it will sample gases, especially noble gases, and trace species that tell you about the planet's origin and how much water it used to have, while also snapping high-resolution images of Alpha Regio, a rugged tessera region that may preserve some of the oldest, most deformed crust. The plan is for launch in the early 2030s, with a probe descent a few years after arrival, basically a one-shot, high-intensity science bomb. One plunge, a torrent of data, and then it's over. Together, VERITAS and DAVINCI give you a powerful combo: global context from orbit plus deep, vertical, in-situ data through the atmosphere down to one key region on the ground. But they are not the only players. Europe is building its own heavy hitter, EnVision, an ESA Venus orbiter planned for launch around late 2031. EnVision is designed to connect the whole system, from core to surface to atmosphere. It will carry VENSAR, a high-resolution synthetic aperture radar, plus a subsurface radar sounder and a spectroscopy suite called VENSPEC, and gravity science experiments. The idea is to watch how the interior and crust are behaving now, see where the planet might still be active, and link that to what's happening in the atmosphere. It's explicitly framed as, why did Venus and Earth diverge so much? The same core question you care about for climate and exoplanets. Here's where the tension creeps back in, though. A key part of EnVision, the VENSAR radar, is supposed to be provided by NASA. That instrument is exactly the kind of thing you want, high-detail mapping down to around 10 meters resolution. But current US budget proposals include deep cuts to NASA's science program, and VENSAR is one of the items at risk. ESA has publicly said they need clarity soon, or they may be forced to find a European backup solution, which would add time and complexity. In the worst case, NASA could end up pulling out entirely, and EnVision would have to reconfigure midstream. So the next part of the story is about those missions we are finally, slowly sending back to Venus, what they're designed to do, and how fragile their future still is. Then you have India stepping in with its own mission, Shukrayaan, officially the Venus Orbiter mission. ISRO has now formally approved it, with a planned launch on March 29, 2028, using an LVM-3 rocket and an arrival in Venus orbit in July 2028, after about 112 days of cruise. The orbiter, roughly 2.5 tons, is expected to operate for about 4 years, studying the atmosphere, the surface, and how the solar wind interacts with the planet's magnetic environment. Designs and papers have discussed an aerobot balloon component as well, a sign that people are seriously thinking about using that 50 to 60 kilometer Goldilocks layer. National science meetings in 2025 show India mobilizing its research community around this mission, which means more instruments, more teams, and more eyes on Venus from yet another spacefaring nation. Stack that all together, and on paper, the 2030s look like a Venus decade. You'd have a new global radar mapper from NASA, a deep atmosphere and tessera probe from NASA, a European orbiter connecting geology and climate with its own radar and spectrometers, and an Indian orbiter adding independent measurements and perspectives. After Akatsuki's long, lonely watch over Venus's atmosphere, which ended in the mid-2020s, this looks like a real coordinated return. But here's the part you can't ignore. All of these missions live in the real world, where budgets get cut for reasons that have nothing to do with science. In 2025, the White House proposed a plan that would have slashed NASA's science budget by almost half and canceled or crippled dozens of missions. Advocacy in Congress may soften or reverse some of that, but the message is clear. The funding environment is unstable. VERITAS was already delayed once because money and staff were pulled toward other priorities. VENSAR's future is uncertain because of the same pressure. Any overruns on Mars sample return or other big flagship projects can easily create a domino effect that pushes Venus missions back or squeezes their capabilities. So even this "we're finally going back" moment sits on a knife edge. You have multiple spacecraft in design and early build phases, you have international collaboration, you have a clear scientific case, but a few bad budget cycles could still thin that list, delay launches into the late 2030s, or force descopes that cut into the science you actually care about. Venus has waited decades for another serious look, and now that the window is finally opening, we're still close to slamming it shut. And that's where you have to zoom out one more time, because these missions are not just about one hot planet. They are about understanding what happens to Earth-like worlds when climate runs away, and about making sense of all the super-Earths and warm Earths we keep finding around other stars. If we blow this chance to really study Venus in depth, we are not just skipping a planet, we are throwing away one of the best reality checks we have on our own future. So the next step is to talk about that bigger picture, how Venus data feeds straight into exoplanet science and into our models for climate tipping points here at home, and why ignoring Venus isn't just a missed opportunity, it's a real risk. How do you look at a sky full of Earth-sized exoplanets and know which ones are real cousins of Earth and which ones are just Venus in disguise? That's where Venus stops being a local curiosity and turns into a template. When telescopes look at other stars, a lot of the planets we pick up in or near the so-called habitable zone are roughly Earth-sized, with orbits that give them a similar amount of starlight. On a simple chart, they look like potential Earths, but physically, many of them are probably closer to Venus, thick atmospheres, strong greenhouse, maybe past oceans that are now gone. To tell the difference, you need to read their atmospheres from tiny changes in starlight, spectra with subtle features. If you misinterpret what a Venus-like atmosphere looks like, you can easily label a hot, suffocating world as Earth-like. That is not just a small mistake. That would completely warp how we count habitable planets in the galaxy. So you need to know, in detail, how a real Venus atmosphere behaves. What are the exact ratios of carbon dioxide, nitrogen, sulfur compounds? How does temperature change with height? How do clouds scatter and absorb light at different wavelengths? How do trace gases like water vapor, sulfur dioxide, or maybe phosphine actually show up in a spectrum? You cannot get those answers just from theory. You need real data from different layers, including that 50 to 60 kilometer band and the high atmosphere where escape happens. That's what lets you build models that you can safely apply to exoplanets. Then there's the question everyone avoids until they have to face it. Where is the line between hot but habitable and runaway greenhouse that never comes back? Venus is proof that a planet of roughly Earth's size and composition can cross that line, and once it does, it stays on the hostile side. It likely started with liquid water and milder conditions. Then, as solar flux increased and greenhouse gases built up, the climate spun into a state where the oceans boiled off, water was broken apart higher up, hydrogen escaped to space, and the planet was left with a dense carbon dioxide atmosphere and almost no water. That is not just a story about the distant past, it is a live constraint. It says there is a tipping point somewhere in the space of how much sunlight, how much greenhouse gas, how much water loss, where a planet stops being able to regulate itself the way Earth currently does. That tipping point is not next century for Earth in any realistic scenario, but over millions to hundreds of millions of years, it matters. It defines Earth's long-term safety margin. If you care about how long Earth can remain comfortably habitable as the sun slowly brightens, you need the Venus data point to narrow down that boundary. You want to know how much extra solar flux Venus got compared to early Earth, how fast water can be lost from an upper atmosphere, how clouds respond when the atmosphere is already thick and hot. Those aren't abstract numbers, they're the edges of our real risk envelope over geologic time. Now, fold Mars into the picture. You have 3 rocky planets in the inner solar system, Earth, Venus, and Mars, all starting from roughly similar raw materials but ending with very different atmospheres and surfaces. Earth, moderate temperature, thick nitrogen-oxygen atmosphere, active hydrologic cycle. Venus, extreme heat, dense carbon dioxide atmosphere, no oceans left. Mars, cold, thin atmosphere, lost most of its air and surface water. When you do comparative planetology, you place these 3 side by side and use them as anchor points for your models of climate and interior evolution. Venus is the extreme hot end. Mars is the extreme cold end. Earth sits in the middle. If your climate model and interior model can reproduce all 3 outcomes under reasonable assumptions, you gain confidence that you're not fooling yourself when you apply similar models to exoplanets or to Earth's far future. If your model only fits Earth and Mars, but fails to get a Venus-like state under Venus-like conditions, that's a red flag. In statistics, extreme outliers test your assumptions. In planetary science, Venus is that outlier. It is the stress test planet. Without it, your theory is under-constrained, and you can talk yourself into a comforting story that might be wrong. There's also a more direct, practical angle. On Earth, people talk about geoengineering, big-scale interventions to counteract climate change. Some proposals involve making the atmosphere more reflective with aerosols. Others involve changing greenhouse gas levels in controlled ways. If you're going to even think about altering a planetary atmosphere on purpose, you need the best possible understanding of how atmospheres respond when you push them hard. Venus is a real-world example of what happens when greenhouse gases dominate and cloud decks become thick and permanent. You don't get to practice geoengineering on Earth at full scale and then rewind if it goes wrong. You have one shot. So Venus, with its runaway greenhouse and reflective cloud layer, is your what not to do reference. It shows you a system where the balance went far beyond the range you want. By studying how radiation, aerosols, and chemistry interact there, you get a clearer sense of how not to oversteer on Earth. That doesn't give you a simple rule, like never add aerosols, but it does tell you in detail how feedbacks can surprise you when atmospheres get thick and hot. When you put all of this together, ignoring Venus stops being just a strange choice and starts looking reckless. For exoplanets, you risk misclassifying hot, dense worlds as habitable. For Earth's long-term climate, you leave one side of the risk curve unconstrained. For basic planetary evolution, you drop the most extreme, most informative data point. You do all that mainly because the missions are hard, the lifetimes are short, and the pictures are less pretty than rovers on Mars. Once you see that clearly, the decades-long gap in serious Venus exploration is not just we preferred other science cases. It's a blind spot in our survival strategy as a civilization. We built whole narratives about habitable zones, climate stability, and planetary futures, while quietly undersampling the one world that shows us how badly things can go on a planet very much like our own. And that circles you back to the core question that started this whole video. If Venus is this important, scientifically and existentially, why did we barely go back after those early missions, and what will it take to finally change that? So when you say we never went back to Venus, the first correction is simple. It's not never, it's not enough. We did go. We threw early flybys past it. We put orbiters around it. We dropped atmospheric probes through its clouds. We even flew balloons in that 50 to 60 kilometer layer. The Soviets landed multiple Venera probes and Vega landers that actually touched the ground and sent back data, even if they only survived between about 20 minutes and 2 hours. On paper, that's a serious record. But when you line that up next to the steady drumbeat of Mars missions, rover after rover, orbiter after orbiter, decade after decade, Venus looks empty. You feel the gap. That's what people are really reacting to when they say we never went back. They're seeing that after the intense burst of activity up to the early 1990s, the follow-through never happened. To answer why, you have to stack every deterrent you've just walked through and see how they line up. Take one planet and push its surface temperature above 460 degrees Celsius, around 860 Fahrenheit. Push its surface pressure up to about 93 bar, like being nearly 900 meters, roughly 3,000 feet, under Earth's ocean. Make the atmosphere mostly carbon dioxide, loaded with sulfur dioxide and sulfuric acid clouds. Run the winds at the cloud tops around the planet in roughly 4 Earth days, while the solid surface crawls around once every 243 days. Then drop that planet into a landscape that rewards missions which are cheaper, safer, and give you years of pretty pictures from cold, solid ground. That combination is the perfect storm. The physics gives you high temperature, high pressure, and nasty chemistry. The dynamics give you super rotation, hard entry, and tricky communications. The tech base is rusty because only one side in the old space race really mastered surface landers there. The budgets favor long-lived missions with simple, hopeful stories like ancient rivers on Mars and oceans under ice. Venus in that environment is an easy target to cut. When someone needs to trim a list, they look at high risk, high cost, low surface lifetime, difficult optics, and Venus drops off the bottom. Underneath that, there's something simpler and a bit more human: the cost of fear. The technology to go back is not science fiction. You have high-temperature electronics based on silicon carbide and related materials in development and early use. You have advanced heat shield materials and entry systems tested on other missions. You know how to build pressure vessels that can handle deep sea levels of stress. You've already flown balloons in the Venus atmosphere once, and modern materials and batteries could only improve on that. Precision radar, spectroscopy, and atmospheric instruments are actually some of the most mature tools we have in spaceflight. What's missing is not the physics or the basic engineering. It's the willingness to put serious money and reputation into a mission that might die quickly and publicly. A Mars rover can fail too, but when it lands and works, you can expect years of output. A Venus lander might give you tens of minutes or a few hours of surface data before the environment wins. If something goes wrong during entry or descent, the spacecraft can be lost completely. That's hard to sell to risk-averse managers. No one wants to be the person who spent a couple of $1 billion on a probe that hits a 460-degree surface, transmits for 20 minutes, then falls silent. Even if that 20 minutes is packed with data you cannot get any other way, the optics look brutal. That fear has a real price. It leads to mission concepts being toned down, stretched out, or quietly shelved. It leads to conservative choices, where agencies go for a safer Mars orbiter or an outer planet flyby instead of a first-of-a-kind Venus lander or balloon network. Every time that happens, you lose a chance to get the extreme data point you actually need for understanding Earth-like planets. On the other side, if you push past that fear and actually commit to Venus in a serious way, the payoff is big. Venus can tell you how Earth-like planets die, not in some abstract model, but in real numbers. It can show you how a world that likely had oceans and mild conditions slips past the point where water can stay liquid into a runaway greenhouse state that locks in for billions of years. It can test whether a planet with a wet past can still host anything in its clouds once the surface is gone. And if not, what chemical fingerprints clearly separate a purely abiotic cloud deck from one shaped by biology? Those are not small questions. They touch on how many truly habitable planets are out there, how long Earth can stay in a bid state, and what lines we should never cross with our own atmosphere. Those are survival-level questions, not just interesting science. So when you hear, "we never went back to Venus," you now know the real meaning behind that line. We did go, but we pulled back before we really understood the place. We let brutal physics, high engineering cost, and an undersold science story combine with marketing concerns. We chose easy worlds with long lifetimes and good visuals over the one world that forces us to confront the worst-case outcome for an Earth-sized planet. The good news is that choice is not locked in forever. Missions like VERITAS, DAVINCI, EnVision, and Shukrayaan are showing that the tide is starting to turn. The phosphine debate, the exoplanet boom, and rising concern about climate have all pushed Venus back into serious conversation. If those missions actually launch and succeed, they won't just tick a box that says we visited a hot planet. They will give you a clearer picture of Earth's possible future, a sharper filter for spotting real Earth analogs around other stars, and a hard limit on how far you can push a planet before it stops being a place where complex life can exist. In the end, going back to Venus is not about proving that we're tough enough to land in 460-degree air again. It's about looking at a world that shows you one way the story can end, and deciding, with data in hand and no excuses left, that you're going to do everything you can to keep your own planet on the other path. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.